Amrapali Patil, Assistant Professor at Department of Physics, Mahatma Phule Arts, Commerce and Sitaramji Chaudhary Science Mahavidyalaya, Varud. From today onwards, we are going to take your online classes because of the COVID-19 pandemic. We are not able to take your regular classes in the college campus to avoid the social gathering. So today this is my first lecture and I am going to teach you your third unit of third semester syllabus of BSc second year. Okay. The name of the unit is Solid State Electronics Devices 1. In total, about 12 marks are allotted for this unit in the examination. So we start the unit. Name is Solid State Electronics Devices 1. These are the outlines for the topics which we will study in this unit. Okay. First one is Introduction to Semiconductor. As the name of the unit is Solid State Electronic Devices, and we know 99% of solid state electronic devices are made up of semiconducting materials. For example, microprocessors used in computers or laptops, small chips or SIMs used in mobiles or phones, LED lights, transistors, diodes, etc. Almost all the electronic devices are made up of semiconductors or semiconducting materials. Hence, we have to study in detail about the semiconductors. So, in this unit, we will discuss about the introduction to semiconductors, charge carriers and electric conduction through semiconductors, what are charge carriers and how the electric conduction takes place through the semiconductors. We will discuss doping. What is doping? Extrinsic semiconductor and energy level diagrams. What is extrinsic semiconductor and their energy level diagrams we will study or discuss. What is drift current in semiconductor? What is mobility and conductivity in semiconductors? What is Hall effect in semiconductor? Semiconducting diodes and its biasing. Okay, these are the applications of semiconductors. How they work, we will discuss in this unit. Light emitting diode, that is LED, and last varactor diode. These are the applications of semiconductors we have to study in this unit. Okay, so these contents are the outline. These contents are outlined for the these are the outlines for the unit 3. So we start from the basics. What is solid? As we know, it is one of the state of matter which has mass and occupies space. We know the 3 states of matter: gas, liquid and solid. Okay, there are 3 states of matter: gaseous state, liquid state and solid state. In gaseous state, the atoms or molecules are separated from each other by comparatively large distances and are haphazardly arranged. Means they don't have a definite shape, and the intermolecular, there is a negligible force of attraction between the molecules due to lack of intermolecular force of attraction between the atoms or molecules in the gaseous state. Okay, in liquid state, the atoms or molecules are closer as compared to the gaseous state, but are still arranged in haphazardly mannered. Still, they don't have a definite shape. they acquire the shape of the container or vessel in which they are filled. In solid state, the atoms are closest, means the atoms are very close to each other. Their constituent particles held closely by strong intermolecular forces. Also, all the atoms have their fixed position, which gives them orderly three-dimensional pattern called a lattice or crystal lattice. Okay, so the solids are which has a definite shape, definite volume, highly incompressible, means they cannot be easily compressed, rigid in nature, cannot be easily modified, constituent particles held closely by strong intermolecular forces, and fixed position of constituents. Particles are fixed. Particles have their fixed position. Okay, and the distance between the each constituent particle is fixed and the same in case of solids. Okay, so this is about the solid. Now there are two types of solids, and this classification is based upon the atomic arrangement and binding energy of particles or atoms, physical and chemical properties of the material, solid material. Okay, so on the basis of these properties, the solids are classified as crystalline solid and amorphous solid. Classified as crystalline solid and amorphous solid. So, crystalline solids. A crystalline solid usually consists of a large number of small crystals. It is made up of large number of small crystals. Okay, or we can say that it is a cluster of small crystals, each of them having a definite characteristics geometrical shape. Each of them means each crystal have their definite characteristic geometrical shape. In crystal, the arrangement of constituent particles is ordered. All particles are orderly arranged. They have a fixed pattern of arrangement. It has a long range order, means that there is a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. This is a crystalline solid. And amorphous solid. Amorphous solids consist of a particle of irregular shape. The arrangement of constituent particles in such a solid has only short range order. Each atom or molecule is not fixed at a definite point in the space at definite distance. In such an arrangement, a regular and periodically repeating pattern is observed over a short distance only. Okay. The arrangement of particles are not repeated periodically. Okay. Amorphous solids have tendency to flow. So these solids are also called as pseudo or supercooled liquids. They have tendency to flow like a liquid, hence also called as pseudo or supercooled liquids. For the crystalline solid. Further, the crystalline material is divided into three categories. One is conductor, insulator, and semiconductor. These are three These are three categories of crystalline materials. One is conductor, insulator, and semiconductor. conductor are those in which large number of free electrons are available for electric conduction. Okay, in conductors they have large numbers of free electrons moving in the conducting materials, so as they move freely in that material and they produced electric current. Okay, examples of conductors are copper, silver, aluminium, etc. Insulators are those materials in which no electrons are available. Second is insulator. Insulators are those materials in which no electrons are available for electric conduction. Means all the valence electrons are tightly bound to their parent atom. Since all the valence electrons are tightly bounded to their parent atom, so there is no free electrons which move in that into insulating material that will moving in that insulating material. So there is no free electrons which is available for the electric conduction, and hence they cannot conduct the electric current. And the examples for insulators are glass, mica, quartz, etc. Third type of crystalline material is semiconductor, a material whose conductivity lies between a good conductor and an insulator. Okay, these materials have conductivity which is lies in between a good conductor and a insulator. Okay, sometimes the semiconductor act as a conductor and sometimes an semiconductor act as an insulator. Examples are silicon, germanium, gallium, arsenide, etc. Okay, these are the classification of crystalline material. So the crystalline materials are classified into three categories: that is conductors, insulator, and semiconductors. This classification is based on their electrical properties. Okay, this classification is based on their electrical properties. Now, the crystalline materials can also be classified on the basis of their energy band diagram. Okay, the classification of solids in terms of their energy band diagrams. So first of all, we have to know about the energy band. What is energy band? So for a single isolated atom, each atom has a specific or discrete energy level. I repeat, whenever the important sentence is come, I repeat that sentence. Okay, so please don't confused about the repetition. Okay, so once again, for a single isolated atom, each atom has a specific or discrete energy level. In case of crystalline solid, the single isolated atom is not possible practically in crystalline solid. Okay, in case of crystalline solid, the single isolated atom is not possible practically. Hence, the discrete energy level is also not possible in case of a crystalline solid, because the crystalline solid is made up of many atoms. Crystalline solid is a cluster of small crystals, Okay, and each atom is tightly bounded with its adjacent or parent atom, and they tightly bounded with the strong intermolecular force. Hence, their discrete energy levels are also get interacted. Due to this interaction, the energy level of each atom is divided into many small continuous energy. I repeat the sentence. Due to this interaction of in between the atoms of the crystalline solid, due to this interaction, the energy level of each atom is divided into many small continuous energy levels with respect to their adjacent atoms. These continuous energy levels are very close to each other, so that they looks like a band. These energy levels are so close to each other, so that they looks like a band. Hence, instead of a discrete energy level of individual atom, there is a energy band. There is an energy band due to interaction of atoms in the crystalline solid. Okay, so this is a energy band. I hope you understand the energy band. Okay, so on the basis of this energy band band diagram, on the basis of this energy band diagram, the crystalline solid can also be classified. Okay, so show at the figure. This is the energy band diagram. This is the energy band diagram in the insulator. Okay, in this diagram, the bottom level band is called as valence band, and the top level band is called as conduction band. Okay, and the gap or the difference between the valence band and the conduction band is called as a forbidden energy band gap. It is denoted by Eg. Okay, so what is valence band? The valence band energy occupied by the valence electrons means the outermost shell electrons. Okay, hence it is called as valence band, since it contains the valence electrons. And the valence band, it is a highest occupied band. Valence band is a highest occupied band. This valence band may be either completely filled or partially filled with electrons. Okay, either completely filled or partially filled with electrons, but can never be empty. Okay, it can never be empty. At least one electron should be present in the valence band. Okay, now conduction band. When the excited electrons in the valence band move to the conduction band, these electrons which moves to the conduction band are called as conduction electrons. Okay, the electrons in the conduction band are called as conduction electrons. When the thermal energy is given to the valence electrons, the electrons get excited towards the conduction band and move freely and conduct electric current. And the valence electron get excited towards the conduction band and move freely in the conduction band, and they are available for the electric current. They are available for the electric current. hence called as, and hence these electrons are called as conduction electrons. Hence the electrons are called as conduction electrons, okay, or also called as free electrons. Now these valence band and conduction bands are separated by the gap known as forbidden energy gap, okay. Valence band valence band and the conduction bands are moved freely. The difference between the valence band and the conduction band are called as forbidden energy gap, okay. The valence band and are called as forbidden energy gap. It is denoted by Eg. When the energy required to lift an electron, energy is required to lift an electron. The energy is required to lift an electron from the valence band, take it across the gap, the valence. The energy required to lift an electron from the valence band, take it across the gap, and put in the conduction band, okay. So this is about the description about the energy band diagram in the insulator, okay. This is the description about the energy band diagram in the insulator. So in case of an insulator, the insulator have the full valence band as there is no conduction electrons in case of insulator. So the valence band is fully filled, okay, and the conduction band is empty. And the difference between the valence band and the conduction band is large, okay. There is a large energy gap between them, between the valence band and the conduction band, and this gap means the forbidden energy gap is about or more than 3 electron volts in case of a insulator. So this is a energy band diagram in conductor, okay. Second, energy band diagram in conductors. For conduction to take place, electron must be given large amount of energy to jump from the valence band to the conduction band in case of a conductor. But in case of a conductor, there is a overlapping of valence band and conduction band. Hence we can observe that there is a no forbidden energy gap in case of a conductor. There is no forbidden energy gap in case of a conductor, okay. Hence the valence electron can easily moved to the conduction band. Hence the valence bands easily move to the conduction band and they freely available for the electric conduction, okay. So in case of a conductor, the valence band and the conduction bands are overlapped to each other, okay, or superimposed to each other. There is no physical difference between two bands, okay. This indicates that there is no physical difference between two bands, okay. No forbidden energy gap can easily jump, the electrons can easily jump to the conduction band. Hence due to the overlapping of the valence band and conduction band, the valence electron can easily jump to the conduction band, which gives the availability of large number of conduction electrons, which gives the availability of large number of conduction electrons, hence they can conduct the electric current. So this is the energy band diagram in the conductors. Now this is the diagram of energy band diagram in semiconductor. This is the energy band diagram of semiconductor. Okay, in case of semiconductor, when at absolute zero temperature, at absolute zero temperature, there are no electrons in the conduction band of the semiconductors. Okay, there are two cases in case of semiconductors. Okay, there arises two cases in case of semiconductors. One is at absolute zero. At absolute zero, there are no electrons in the conduction bands of the semiconductor, and the valence band is completely filled. Okay, so in case of absolute zero temperature, the valence band is completely filled and the conduction band is empty, and hence we can say that at absolute zero temperature, the semiconductor acts like a perfect insulator. Okay, but as the temperature increases, the width of the forbidden energy band gap decreases. Okay, as the temperature, this forbidden energy gap decreases with increase in temperature. Okay, hence the some of the electrons in the valence band can jump to the conduction band, so that as increase in temperature, the forbidden energy gap decreases and the valence electrons can jump to the conduction band, and the conductivity of the semiconductor increases with temperature, and hence the conductivity of the temperature increases with the temperature. So in semiconductors, the energy band diagram contains, so in case of a semiconductor, the energy band diagram contains conduction band is partially filled and the partially filled valence band. Okay, this is a energy band diagram in the semiconductors. We have to remember that at absolute zero, the semiconductor behaves like a insulator. As temperature increases, this forbidden energy gap decreases and the valence electrons jump to the conduction band, so they can act as a conductor also. Okay, so this is about the introduction to semiconductor. Okay, I hope you understand the topic. Now we stop here and the next topic will be covered in the next lecture. Thank you.